Oh, yeah, now it did.
Picture.
Oh, we got a picture. All right. So let's start with the sine function. Okay. We're going to start with something simple. Now, I'm going to ask you a really simple question. Okay. Let me start with a simple unit circle. If I said the sine of 30 degrees or pi over 6, what's the answer? It's a common name. If you don't know, it's probably one you should know, and if you don't know it, you have a calculator.
Half?
1/2. Okay, eventually that's what. Yeah, should you know that one? Yeah, probably, because it's a common angle. Okay, great. So if I said solve sine of x equals 1/2, then the answer is obviously what?
30.
Actually, you would give a radian answer in this case. The answer is obviously pi over 6, right? But what if I went around an extra time? That'd be 13 pi over 6. What if I went backwards one whole time? That'd be negative 11 pi over 6. How many ways can I represent this position on the unit circle?
Infinite?
Yeah, just keep adding multiples of 2 pi, and won't I keep ending up at the same place? So do you agree there's an infinite number of angles that will put me here? Oh, and by the way, what about that one? Oh, so if you go back, you remember the answer to this was pi over 6 plus 2k pi, comma, 11 pi over 6 plus, you remember this? Oh my gosh, so what we're giving are the positions, and then the plus 2k pi is what's called coterminal. You're stopping at the same place. So not only are there an infinite number of answers, there's actually 2 different places. But I kind of want to get the first one back again. There's a problem there, isn't there? You see, the sine is a function that can only return one value. But if I said how many places return to half, there's an infinite number of answers. I would really like to work it so there's one. So let me go back in time and remind you of something that you've seen before. Okay, consider y equal x squared. Okay? Now, if I said, what's 3 squared? Obviously, that's 9. So if I said, when is x squared equal to 9, then obviously the answer is 3.
Or minus 3.
Or negative 3. Oh, I have the same problem, don't I? There's only one output, but maybe there was more than one input that produced that output. So that leads to a problem. Everybody knows what a function is. A function is if I give one input, there can only be one output. If we were talking about a graphical representation, right? That's not a function because there are inputs that produce multiple outputs. And what's the visual test, do you remember?
Vertical line?
It's called the vertical line test. If I could draw a vertical line and it passes through more than one point, that means that one input can do multiple outputs. That's bad. Imagine a calculator where you entered a number and you got an answer, and then you entered the same numbers and got a different answer. Would you trust your calculator ever again? If the same input produced different answers? No, that would be very bad. So this is not a function because one input produces multiple outputs, potentially. This is a function. Every input produces one output, but one output can come from multiple inputs. So although this is a function, we say it is not, you remember what type? It's not 1-to-1. Sorry. Oh, 1-to-1 means one input produces one output, and every output came from exactly one input. So there are rules for 1-to-1. You can tell by looking at a picture if something's 1-to-1 or not. Both of these are 1-to-1. One's always going uphill. The other one's always going downhill. They are what is called monotonic. Mono means what?
One.
One. That literally means one direction. Doesn't matter if it's uphill or downhill, it's only going in one direction. Is the parabola monotonic? No, it turns around. Oh, so if I have a function that's not monotonic, that means it's going to turn around. It will not be 1-to-1. This is not 1-to-1. But what if I wanted it so that if I gave you a number, you'd tell me it only came from one? Well, here's what we do. Right now, what is the domain of this? It's negative infinity to infinity, and what's the range?
0 infinity.
Now, whether you remember this or not, to come up with an inverse to anything is really easy. You just swap the roles of x and y. This is my function. What is the inverse?
X equals square root 1.
No. I just said, the only way you can do an inverse is you swap the roles of x and y. That's it. Anything else would be incorrect. That's it. You don't do any algebra. You swap the roles of x and y. Is this a function? No. So if your original function is not one-to-one, its inverse will not be a function. And here's an easy way to think about it. If your original function fails the horizontal line test, it's not one-to-one, which means its inverse will then fail the vertical, because that's how you do inverses, right? You flip them over the line y equal x. Can I restrict, oh, by the way, what's the domain and range of this guy? Even though it's not a function, it still has a domain and range. What's the domain and range of this guy? Well, that's easy. Just swap those two, right? I want to do something to the first function that makes its inverse also a function. This is called restricting the domain. Now, you may or may not remember this. You probably did this in a lower level class, but you may not have understood why you were doing this. You're doing this primarily for what we're going to do with the trig stuff. So what if I said I'm going to restrict the domain of my x, y equal x squared to just this? What if I restricted the domain to that? Then what would that do to its inverse? It would restrict the range to that. Are these now both one-to-one functions?
Mm-hmm.
In fact, the second one, we no longer will call it x equal y squared. We'd call it y equal, you said earlier, square root. Oh, the square root is not the inverse of the x squared. No, it is not. But if I restrict the domain, it is. That's huge. I need to restrict the domain to make this guy here one-to-one. That way, now when you give me one input, I give you one output, and if you gave me the output, I can give you the input it came from, because we restricted it to positive numbers. So let's go back to the sign, because this is the same reasoning we're going to do with this stuff. Okay, we all know what a sine wave looks like. Right? Forever and ever and ever does this kind of thing. It's going to bounce between -1 and 1. It's going to complete a whole cycle every 2 pi. We're not going to do anything weird. We're not going to do phase shifts or amplitude changes or change the cycle. Pretty simple. But if I said, what is the inverse of this, then would it be safe to say the inverse probably is going to be something like this, which is clearly not a function. We just demonstrated that right here. Infinite numbers. So can I restrict the domain of my original sine wave? Right now, what is the domain of the sine wave right now?
Negative infinity.
Yeah. In other words, there's no restriction at all, is there? So the domain is negative infinity to infinity, and the range is -1 to 1. Look what I did with the y equal x squared. I kept the range the same. It was still 0 to infinity. I just shrunk the domain to where it was monotonic. So I don't want to mess with the range, but can I shrink the domain so I still go from -1 to 1 without changing the direction? Yeah. What if I only use that much? What if I basically went from here to here? Then wouldn't the inverse still be a function? Which would mean, yeah, one input still gives me one output, but one output would only come from one input, and that's what I want. Okay? So if I restrict the domain here to be -pi/2 to pi/2. -pi/2 to pi/2. That's the key. Listen. Now, what does an inverse graph look like? It looks like the original graph. This is absolute across the board, doesn't matter what you're talking about. Whatever the original graph is, if I flip it over the line y equal x, because I've swapped the roles of x and y, that's what an inverse looks like. If I do this, we agreed that the inverse will still be a function. And we call the inverse the inverse. My new function is going to be y equals, now if you're going to write it out and you were going to do this on a computer, you'd say y equals inverse sine. The way we write it, and this is often confusing to people. Remember, if I want to raise sine to a power, and I want to put the exponent there, it only works if the exponent is a positive integer. We talked about that. You can't raise sine to the -2 and put a -2 there. You can't raise sine to the 1/2 and put a 1/2 there. No, only sine squared, cubed, 4th power. In all situations mathematical, there is no exception to the following. This always means F inverse. In no situation does it mean reciprocal. The inverse of a function is not the reciprocal, period. Ever. But when I ask an educated math person what's an inverse, the first thing they tell me is a reciprocal. So if I want to do an addition, I use the reciprocal. If I want to do a square, I use the reciprocal. If I want to undo a logarithm, I use the reciprocal. Think of every function that exists, and it's never going to be the reciprocal, is it? No, the reciprocal is the inverse of multiplication. But there are an infinite number of operations that aren't multiplication. Right? The reciprocal is called the multiplicative inverse, but the opposite sign is called the additive inverse. Oh, the logarithm is called the exponential inverse, and so on. The root is called the, we can go on forever and ever and ever. So inverse sine is not sine. The sine function takes as input the angle. It returns as output the ratio. That's why it's between -1 and 1, right? It's the y value on the unit circle. The inverse sine takes as input the ratio. It outputs the angle. So going back to the beginning, and by the way, do this on your calculator. Your calculator would need to be in radian mode, but for the purposes of what we're doing, I'd actually put the calculator in degree mode. The reason is when you get a radian answer, of course, all of you know, like, pi over 6 radians by heart, right? You all know the decimal. Agreed? Everybody can do pi over 4 radians in their head really quickly, give me the decimal. Put your calculator in degree mode when you're doing this. Because looking at a decimal answer for radians is really not helpful to you. You don't recognize that. So if I said the inverse sine of 1/2, it is equal to pi over 6. Or if I'm in degree mode, my calculator is going to spit out 30 degrees. But it's not an infinite number, and it's not two different positions, it's exactly one answer. Because if I restrict the domain for the original sine function, now I can define the inverse function over this very narrow range of values, but that's it. So an inverse function only exists if the original function is 1 to 1. But a sine isn't 1 to 1, so I restrict the domain to the smallest. By the way, could we have used a different interval? Could we have gone maybe from here to here? Or from here to here? Yeah, this just is the most logical because it includes 0. This one just makes the most sense. That's why we've universally agreed, right? The Universal Math Council gets together every few years and we argue, well, let's change the sine function. Nah, let's leave it alone. So we're going to leave it alone. So forevermore, that's what it is. So that's what the inverse is. We're going to next day talk about the derivatives of the inverse functions, but we need to know what they are and what their restrictions are right off the bat. Now, keeping up with this concept, what about the cosine function? Okay, so now the cosine function is a little bit different. It looks like a sine wave. I need a different guy. Oh, I had one. I think it was this one with the red cap. Okay, so the cosine function, I need to do the same thing I did with the sine. I need one portion that sweeps out all possible values from -1 to 1. I'd like to include 0 in that. Can I go from -pi to pi over 2 to pi over 2 like I did with the sine? No, because that's not 1 to 1 and I don't have any negatives. So really I need to go here, or here, or here, or here. Which do you think is the most logical one? Maybe the one that starts at 0 and goes to here, because they're all positive. I could have done this one, but then they're all negative. So we choose this one. So if I restrict the domain of the cosine function, let's go back to y equals cos x. If I restrict the domain to 0 to pi, then the range will definitely be -1 to 1. But now I can define an inverse function. And the inverse will be a function, and now I can define inverse cosine. Inverse sine will always return an angle between -pi/2 and pi/2, or between -90 degrees and +90 degrees if I'm in degree mode. Inverse cosine will always return an angle between 0 and pi. I can't return an angle outside of that range of values. Okay, you with me so far? So, let's do an example of something. This is a problem that you did in baby trig, and I would hope you did in pre-calc also. You remember this problem? Tells you the sine of an angle, and I give you a number. And by the way, you do need to know what quadrant it is, because that affects the plus or minuses. Here's a problem from both trig and pre-calc. And there's only one convenient and easy way to do this. You draw a picture. Now what's the picture I'm going to draw? SOHCAHTOA. Sine is 2/3. Can you fill in the numbers for me? Don't think unit circle. I don't want this to be a 1. I don't want any fractions. I want it to be easy. Sine is 2/3. Where's the 2 going to go? Is this a so, a ka, or a toa?
So.
It's a so.
Opposite.
Where's the 3 going to go?
Quadrant.
So what goes here? It's right track. So break out your computers.
Root
Root 5.
How about root 5? Yeah. Right? 3 squared minus 2 squared. Can I now answer all of these questions? Again, keep on the SOHCAHTOA. Okay, so what's the cosine? Root 5 over 3. Ka. Tangent?
2 root 5.
2.
Secant.
3 over 2.
Really helps to know what these are. Well, what's the secant the reciprocal of?
3 over root 5.
Cosine.
It's the reciprocal of cosine, so it's 3 over root 5. Cosecant, 3 over 2, and cotangent,
Root 5 over 2.
did you do a single calculation to find these? No, you just used their definitions. Does that problem look vaguely familiar? It's a problem that you did way, way, way back when in baby algebra. Now, why did I need to know what quadrant it was in? Could it have been in the 4th quadrant? No. But it could have been in the 2nd quadrant. Oh, the sign is positive in both the 1st and 2nd. Well, why would that have mattered? Because the x's would have been negative in the 2nd quadrant. So in other words, half these answers would have been opposite sign. You had to know the quadrant. But that's for the plus and minus. But the way I did this was simple. There was just nothing about this that was terribly complicated. Okay. Let's do a similar problem, because this is where this is going. You say, well, I can do this all day. Yeah, like Captain America, right? You can do this all day. The cosine of theta, let's say theta in the, this time we'll go theta in the 4th quadrant, just for excitement's sake. And let's say the cos, let's leave it first, sorry. I'll do 4th later on. 1st quadrant, and the cosine is how about I don't know, 1/2 x. In trig and pre-calc, you always did this with constants. We're in calculus now. You're never going to do this with a constant ever again. The last one I did was the last one you'll ever use a constant. Nope, you're going to do this with variables. Because these are functions. These are not values. Can I still do this problem the same way I did the last problem? The question is the same as this one. I want to find all the pieces. Well, I can't answer any of these unless I have the correct triangle. So now I want the sine, I want the tangent, I want the, I'll do the secant first. The secant, the cosecant, and the cotangent. If you can find one of them, you can probably find all of them, but it's good practice because you got to remember those definitions. Ooh, what goes where? I really don't want any quotients in my triangle if I can avoid it. Because it's not that it's wrong, it just makes the algebra more complicated when I'm doing roots of things. If the cosine of theta is 1/2 x, can I think of it as x over 2? It's a ka. Where does the x go?
Adjacent.
Where does the 2 go?
Adjacent.
What goes here? I'll do my part. So, are you okay with 4 minus x squared? What do you think? Is that okay? If the cosine of theta is 1/2 x, what's the sine of theta? It's actually easier to write like that. What's the tangent of theta? Thinking too much. It's a TOA. Is that right? Then we can finish the rest of them. Was this harder than the last one? Should be exactly the same as the last one. You just happen to have a variable in your answer, which is actually going to be the norm. Because the way you found the answer was exactly the same. You said, let me make a right triangle where there's no, those numbers fit, and then I can answer all the rest. The only twist I'm going to throw on this is maybe give you a different quadrant, and then you're going to see that doesn't actually make it harder. Not at all, it turns out. So if I gave you something that wasn't a constant, but it actually had variables in it, could you still finish out this process? Yes. And that's the part we need to do, because when we do the calculus of the inverse trig functions next day, that's what we have to have. We have to have variables in there. Otherwise, we'd be taking derivatives of constants. We need to take derivatives of functions. Right, so like function of x kind of stuff, okay? Cosine was easy enough, but the most important by far of the inverse trig functions is not those two. It's actually the tangent. This one gets way more action than the sines and cosine. Sine and cosine are common for calculating, but for inverse tan is way more complicated. Or maybe, sorry, way more common. Now, part of the reason you did all that graphing way back when. I had a conversation earlier with another calculus professor, and you guys know that we've eliminated everything below pre-calculus, and pre-calculus is going very, very soon. It's a statewide thing, AB 1725, it's evil. People who are not educators are deciding, right? So you can graduate from high school now with remedial algebra, like the one you probably had in 8th grade, as your highest level of math, but everything below calculus is being eliminated. So pretty soon there's nowhere in California you can take a below calculus class. So what happens to those folks? There's all the in-betweens have been removed, and so if you don't have it in high school, it's not going to exist in college anymore. That's kind of a scary thought. So one of the professors I was talking to talked about trig is pretty much gone now, and 116, which is the pre-calc for business calc, that's going now because state doesn't require it anymore. But they were saying there's a significant amount of the stuff you do in a trig class is a complete waste of time. And I agree. Do you remember our first class? It took me about 22 minutes to review all the trig you ever needed to know in your entire life in order to do calculus. It didn't involve graphing at all. It involved the awareness of your unit circle and all the other stuff. But an awareness of what a graph looks like is very useful because you might see it and you want to recognize it, plus you want to be able to manipulate it. So the tangent function is a very cool function. Does this look familiar? What makes the tangent function different than the other ones? I got asymptotes. It repeats itself infinitely many times. And it's pi wide. So from negative pi over 2 to pi over 2, from pi over 2 to 3 pi over 2, 3 pi over 2 to 5 pi over 2. Forever and ever and ever and ever. I need to restrict the domain for the tangent. Probably the easiest choice of all. Why don't I go with that one? Right? The range is all real numbers, and this one's passing through the origin. So does that seem like a good one to look at? So the domain that we're going to do, we're going to go with negative pi over 2 to pi over 2, which is similar to the sine. The sine was closed. Tangent can't be closed because they're vertical asymptotes. If you do the tangent of pi over 2, that's actually undefined. You're actually doing 1 divided by 0 at that point. So on your calculator, if you put in degrees and you do the tangent of 89.9999999 just for fun, you're going to get an astronomically large number. But if you do the tangent of 90, it's going to say error. Okay? But the range of this is all real. So inverse tan is interesting. Inverse sine, inverse cosine, I can only input numbers between -1 and 1, but for the inverse tangent, I can input any real number. Cool. So if I restrict the domain to just the middle guy, then the inverse tangent looks like that. I can input any real number for inverse tan, and I'm going to output something between negative pi over 2 and pi over 2. That's very, very handy now, isn't it? Okay, so on your calculator, if you did inverse tangent, put the calculator in degree mode, because I want you the answers to make some sense to you. Input a really large, input like 1,000,000. Do inverse tan of 1,000,000. Be in degree mode first. 1,000,000 is a pretty big input, right? It's a pretty big ratio. So on this graph here, I'm asking you to think of a y value that's 1,000,000 units high. So on this graph here, I'm asking you to put in an x value that's 1,000,000 units. It's easily in the next room, if not beyond. What angle did it spit out?
89.9.
A lot of 0.9s?
43.
A lot of 0.9s. Oh, and that makes perfect sense, doesn't it? It's really close to 90 degrees. Is there an upper limit on what you can input? No. There's no upper limit. You can just keep getting bigger and bigger, and that answer is going to keep getting closer and closer to 90 degrees. You're never going to get 90 degrees back again because that's an asymptote. But that's kind of cool, isn't it? So inverse tan returns an angle between negative pi over 2 and pi over 2, just like inverse sine, except inverse sine can actually give you back the endpoints. Inverse tangent is an open interval. Those are the big three. I'm going to show you when we do the calculus. You're never going to do inverse secant, inverse cosecant, or inverse cotangent. There's no need to, because there's a simple identity that relates them. And it turns out, I'm going to show you next year, you're not actually even going to do inverse cosine for the most part. It's really inverse sine, inverse tangent, and then inverse secant. So I'm sorry, I said cosecant and cotangent you're never going to do. But the cosine and the sine go together. The cotangent and the tangent go together. The secant and the cosecant go together in terms of the inverse part. So that is next day. So now I'm going to change my original questions. We'll go back to numbers for a moment. I would like you to find the tangent of the inverse sine of -3/7. Before, I told you something and I told you quadrant. Now I'm not asking the question that way. Now you could do this on your calculator, but the number you get on your screen won't be meaningful. It'll be irrational and you won't be able to tell what it is. I want to attack it the same way I did that one. How am I going to do that? This is your theta. Inverse sine of a ratio returns an angle. And now I want you to take the tangent of that angle. So how do I read this statement right here? This means that the sine of theta is equal to what?
7
How about -3/7? You can't read it any other way. The inverse sine of -3/7, I'm calling that my theta, so the sine of theta must be -3/7. So I just need to make a picture. Now, inverse sine, we said, only returns angles in the first and it's from -pi/2 to pi/2. -pi/2 to pi/2. So first and fourth. Not first and second, first and fourth. Oh, so what quadrant is this in? Inverse sine of a negative number. I can't get a negative ratio in the first quadrant, so I must be in the fourth quadrant. If you want to think it like that, there's my angle. I still want a right triangle. So what goes where? Well, sine SOHCAHTOA. Well, the hypotenuse is never going to be negative. Would it be safe for me to say, call that 7? In other words, you're going down 3. So in other words, think of that point right there. So this is where the -3 would be, wouldn't it? I'm -3 in the y direction. Because if I was +3, I'd be up here. It goes here. Square root of 40. I'm not sure why even one of you is waiting to do I'm going to let somebody else make the wrong answer. Should I expect you to do that? Yeah. That's not calculus. That's not pre-calculus. That's not intermediate algebra. That's actually pre-algebra. Sorry, but telling me what that length is using Pythagorean theorem, that's not answering worries me. Not answering worries me because you're saying I don't know what I'm supposed to do, and this isn't our first problem. This is not our second problem. It's not even our third problem. Yeah, that should be a no-brainer. This is not remotely close to this class. This is low. But don't wait for everybody else to answer the question. The question is now, what is the tangent of this angle? I don't want the other 5 functions. I just want the tangent.
-3 over root 40.
-3 over root 40. My angle had to be in the fourth quadrant. And we know that the tangent of a fourth quadrant angle is also negative. So that's a good thing. I'm going to change the question slightly. I would like you to tell me, I don't know, just for fun, the secant of the inverse sine of -3/7. Is it the same picture? Yeah, because the picture was only to do with this. Now I want the secant, just for fun.
7 over root 40.
First of all, is it positive or is it negative? I'm in the fourth quadrant. The cosine and the secant are both positive. By the way, if it helps you, if you're going, I'm not comfortable with secant, then find the cosine first and just take the reciprocal. That's an easy way to do it. What's the cosine? So what's the secant? By the way, that's a really simple way of doing things. Everybody's okay probably with sine, cosine, and tangent. The other 3 are a little more iffy because you don't use them as much. Well, figure out the one of them and then do the reciprocal of the other one if you know. But that means you have to know that cosine and secant are reciprocals. If I don't know that, then I'm in trouble because then I'm going to do a different angle, different thing. But was that question hard? Not once I have the picture. But notice I asked it different this time. I used an inverse function in order to ask the question. So we're going to do a couple more of those. This is the part I need you to really master. This is not even like calculus. This is just algebra, but we're going to be doing the calculus very soon, and we're going to be doing the calculus of things that look like this but have variables instead of numbers. Only one variable. All right? So how about we do the cosine of the inverse tangent of, let's do something horrible. How about 3 over x? Awful. Now, is 3 over x an angle? Or is it the ratio?
Ratio.
Inverse tan of a ratio returns an angle. So, just like on the last problem, I want you to think this is your theta right there. So, I'm going to show you a way to rethink this question that might make it a little simpler. Find the cosine of theta when the tangent of theta equals what? 3 over x. Is that the exact same question? Yeah. But is it a little easier if I look at it in those terms? Probably, because now the triangle you're about to draw will be a heck of a lot simpler to interpret. I didn't tell you what quadrant you're in. Huh. We'll see if that actually matters. Okay? We'll see if that matters in a moment. But I never said what quadrant you're in. Turns out it won't matter. You get the same answer anyway. Okay, so again, inverse tangent of 3 over x returns my angle, so the tangent of the angle must be 3 over x, and then I want the cosine of that same angle. So, I'll draw a first quadrant picture, and then I'll say, what if it's not first quadrant? By the way, if it's not first quadrant, then what quadrant must it be?
Third.
Inverse tan returns which two? Hopefully you wrote it on your notes. It was this whole area of the board a minute ago.
First and third. Or inverse one?
No inverse trig function returns third, but
First and fourth.
first and fourth, negative pi over 2 to the power of 2. First and fourth. Oh, yes. Now, that's important that we get that one right, because otherwise I'll do all the work correctly but give an incorrect answer. Inverse sine, inverse tangent return first and fourth. Inverse cosine returns first and second. Okay. What goes where? Well, this is a TOA, right? TOA. Where's the 3 go? Vertical, horizontal, or hypotenuse? Vertical. Where's the x go? So what's the hypotenuse? Does it matter if I say 9 plus x squared or x squared plus 9? Nah. Most of you probably would say x squared plus 9, but it actually makes no difference. So what is the cosine then? Cosine. Ka. You gotta spell it right though, don't you? There's no K in ka. It's x over, no, or is it? Ka. There's a lot of, I think it's this, no, you know it's this. Now here's the cool part. If x had been negative, if x, in other words, if this was a negative ratio, then we would have been in the fourth quadrant, wouldn't we? If the ratio had been negative, but I'm still going to get the same final answer. Okay. The nice thing about these is you're going to get the same answer. So I say when you draw the picture, just always draw the first quadrant picture because it's not going to actually change your answer, you know. But there's one situation and one situation only, and it actually involves the secant, which is kind of goofy. So now I want to go over the secant because that's the weirdest one. Because when we do inverse secant next day, that one is the only one that can be a little bit tricky. Now, you don't draw a lot of secants and cosecants. Cotangent's easy. It looks just like tangent, just shift it. Right? And it's also backwards, but it's the same kind of feel. Secant and cosecant. You might remember doing this in a trig class. The way you draw a secant is you start by drawing a cosine. Some of you might remember this. Okay. Secant is the reciprocal of cosine, which brings us a problem right about here, doesn't it?
Yeah.
Oh, I'd be undefined, which means I'm going to have a cosine is exactly 1 here. Do you agree? So its reciprocal is also a 1. But the cosine is getting smaller and smaller and smaller, which means its reciprocal is getting bigger and bigger and bigger. How about down here? How about over here?
Ew.
Does this ring a bell to anybody? You go, oh yeah, I didn't sit there and plot points and all that. I just took a cosine graph and I did this forever and ever and ever. Okay, great. That's what a secant looks like. I need to restrict the domain. Now this is tricky. And this is, believe it or not, the only area that I'm aware of in calculus where there's actually not universal agreement. This is strange. Some textbooks, I'd say it's probably like about 3 to 1, but some textbooks will actually give a different domain restriction. And the reason that's important is it actually changes the derivative. And I don't know why, but this is the only area I'm aware of there's not absolute agreement. Now, I think it's easy if I just go back and look at the cosine. When we restricted the domain of cosine, we restricted it from 0 to pi. If I restrict this from 0 to pi, I'm getting this piece, and I'm getting this piece. Everybody see that? Is that every possible y value that this will sweep out? Because I'm just repeating it on that side, I'm just repeating it on that side. So if I go from, this is 0 to pi, by the way. If I go from 0 to pi, I'm sorry. This is pi. If I go from 0 to pi, I've swept out every conceivable y value that secants can sweep out, and then there's the one discontinuity here. Some textbooks, though, strangely enough, will go from here and then maybe something over here. Just, in other words, doesn't really make a lot of sense to me. They'll use a different interval that isn't logical completely. This is the only one that ever made sense to me. I'm going to go from 0 to pi, not including pi over 2. Because the cosine went 0 to pi, and I've swept out every possible value. Secant of pi over 2 is undefined. Just like tangent of pi over 2 is undefined, because both of them have a cosine in the denominator, and the cosine would be 0 there. So the secant's a little bit wonky, but if I restrict the domain to that, then I can define the inverse secant in this way. So inverse secant. By the way, when I take the secant of an angle, I'm either going to get a number that's 1 or more, -1 or less. I will not get any value between -1 and 1, will I? So the inverse secant is going to take the inverse secant of a ratio that's any real number except between -1 and 1, and then it's going to return an angle between 0 and pi. That's the only one that's just a little on the tricky side. You're not going to make mistakes because of it, but it's a little trickier. But when we get to the calculus, none of those things are going to prevent us from doing the calculus. The calculus is actually very clean. When we do the derivatives of the inverse trig functions, there's no trig in the derivatives. What was the derivative of the logarithms? Right, 1 over the function. There's no exponential or log in the derivative of the natural log. Right, it kind of went away. I got something really clean. Well, turns out the derivatives of the inverse trig are just simple functions. And they look like simple functions, but I can't tell you what they are. We're going to discover them next day. So let's continue on this crazy path. All right, I want to do the tangent of the inverse tangent of, how about 3x squared minus 4? Yeah, the tangent of the inverse tangent of 3x squared minus 4. You have an answer?
Wouldn't that just be 3x squared minus 4?
Yes, it would be.
Not
Why?
that. They cancel?
Not undo each other. That cancel, that sounds like a multiplication. They undo each other. Like e to the log, they undo each other. That is kind of a trick question. The tangent of the inverse tangent of thing is thing. The sine of the inverse sine of thing is thing, on and on and on and on. The e to the log of thing is thing. Log of e to the thing is thing. They undo each other. So sometimes we kind of forget the role of an inverse. So I'm going to go backwards. In the upper level classes, the higher you go, the more often you review the most basic things in mathematics. There are exactly 11 properties of algebra, things you can do to solve an algebraic equation. 5 addition, 5 multiplication, and then 1 extra one. There's, think of it, commutative, associative. Commutative means I can rearrange, associative means I can regroup. There's identity, there's inverse, and then the most important one that you guys have not usually used a whole lot is called closure. That becomes more important later. Closure is when you take 2 things from the same set and combine them and you get back something from that set. And that becomes more and more important later on. Same 5 apply to multiplication. By the way, none of those apply to subtraction, none of those apply to division. No commutativity, no associativity, there's no identity, there's no inverse. What's the 11th one? The distributive property. That's where you add and you multiply at the same time. Those are the 11 properties of algebra, and if I can do those, that's how we justify undoing and doing things, all over the place. So we're going to apply all of those to these kind of things, but inverse is really the key. Identity and inverse always go hand in hand, mathematically speaking. You don't have one without the other. Okay, I'm going to write it. I brought my checkbook today, and I'm going to write a check, and I'm going to sign it, and I'm going to give everybody a check. And my check, a physical act is taking place. I'm going to give you all a check for $0. And your overall standing will remain the same, because 0 is the additive identity. An identity is an operation that leaves something unchanged. Now, how many have a job where your pay increases or percent increases rather than just straight up dollar increases? Anybody have one of those? Yeah, that might be a 5% increase or 10%. So the more you make, the bigger your increase. I work for a district that when I get a raise, which is not very often, I think I had one like 6 years ago. No joke, I've been here too long, there's nowhere to go. My raises are a whopping 2.75%. That's the highest rate. Not quite keep up with inflation. So what they do is they take my paycheck, they don't multiply it by 2.75, they multiply it by 1.0275, and that's my increase. So what I'm going to do is I'm going to increase everybody's score in this class. I'm going to multiply. So I'm going to multiply yours by 1.2, 1.5, 1.3. I'm going to multiply yours by 1. Something took place, but your overall standing didn't change. Why? Because 1 is called the multiplicative identity. Oh, 0 is the additive identity, 1's the multiplicative identity. Okay, an identity is an operation that leaves something unchanged. Okay, what is an inverse? An inverse is an operation, not an identity. Not even like an identity. It's an operation that undoes another operation. So my role in life, I tie shoes. That's what I do. I see your shoes are untied. I go over and I tie your shoes. Noelle here, she's my inverse. What does she do? She unties shoes. She's not my reciprocal. So your shoes are untied. I go over, I tie them, and then she visits you and she unties them. 2 different physical acts took place that changed your standing, but overall, you're exactly the same as you were when you started. Because in inverse, when something and its inverse both act, the result is as if an identity took place. One does something, one undoes that thing, going back to the original. Both change. So I have a quantity, 3x squared minus 4, and now I'm doing the inverse tangent of that. Way different. That's not even a similar mathematical statement. But now I'm taking the tangent of that, undoing it, bringing me back to the start. So the fact that I got the original thing means these together acted like an identity took place. Nothing changed. Those are absolutely astronomical concepts, and the farther you go in math, the more common you get. But we always think about them in sort of an arithmetic standpoint. But in general, just anything that undoes. And so that's why I like to use examples that aren't actually mathematical, right? Shoes, tying and untying, they undo. So anything that undoes something would be technically its inverse, okay? So in baby algebra, how do you undo an addition? You add the opposite sign. How do you undo a multiplication? You multiply by the reciprocal. That's where reciprocal would undo. But if I want to undo a log or an exponent or anything else, I use the inverse function of that thing to undo it if the inverse itself is a function. Ooh, got to be careful. An inverse just means I swap the roles of x and y, but an inverse isn't necessarily a function. Only if the original function was what? 1 to 1. What's the word? You guys remember?
Monotonic.
Monotonic. That's a good one to know because mono you see a lot. Okay. Now I go through this. This is a class that we're probably ready for this. When I teach remedial algebra, or when I used to teach remedial algebra, we don't have it anymore, I would spend about an hour going over prefixes. And what I mean is going over prefixes that you run into in math all the time, but actually probably more often in chemistry. Anybody in chemistry here? You know, so you know what a parabenzoic acid molecule is, you know. I said something really important. So one of my favorite, my wife brought an article several years ago, and I brought it to the class, it was awesome. It talked about the dangers of dihydrogen oxide and how many people die per year of dihydrogen oxide, and on and on and on. And I'm reading this article to the class, and I'm like, why is it even legal? Why don't we eliminate dihydrogen oxide?
Oh.
What's dihydrogen oxide?
H2O.
Water, yeah. And that was the fun part of it, it's water. But if I don't know that, right? Carbon monoxide, carbon dioxide. One you exhale, one comes out of your exhaust pipe. One is harmless, one will kill you. But if you don't know which one is which, you're in trouble because it's based on understanding the Latin. So you guys see that's what I'm saying. So you can't do the chemistry very well if you don't know the prefixes. But I would talk to the chemistry professors, and I say, in chemistry, nomenclature is so astronomically huge. In fact, organic chemistry is mostly nomenclature. But when do you teach them this? They go, we don't teach them that. They learn that in math class. And you've all had math classes where you spent significant time learning all of the Latin prefixes to all the words? Probably not. So I would do this in my remedial algebra classes because we would work with simple geometric shapes. But do you know the difference between a pentagon and a hexagon and an octagon and a decagon? And only if you know what the prefixes mean. And believe it or not, most people don't. So what I would do is take some time, because even in a calculus class, and even more so in Calc 3, we use the prefixes all the time. And everybody sits in the front row and goes, oh yeah, okay, I have no idea what that is because I don't know. So I usually like going through the easy ones, like 1 through 10, and I'll use English words that you can relate to. So, for example, by the way, is this stuff you should know? This is stuff that's actually absolutely crucial in every math and science class you will ever take, and probably most of the ones you have taken. How many are currently taking chemistry? Do they expect you to know all your prefixes and what they mean? Yeah. Are they teaching them to you? Probably not. So where are you learning these things? So I like to do one. There's only two. Okay, you got those animals with one horn coming out of them, or you have the one wheel thing. Uni. Uni means one. Think all and on and on and on. Oh, by the way, we're finding out more and more from the Marvel universe that there's not just one. So what is the Marvel universe referring to everything now as? The multiverse, which I think is eminently cool. I just found out recently from Doctor Strange that every time I have a dream, it's just a different version of me on another universe. And as whacked out as that is, it is kind of cool though, isn't it? Okay, what's another one that means one? We just did it. Mono. Far more common. Okay? There's only one entity, there's only one business selling something.
Monopoly.
It's called a monopoly. Yeah, that's what the game is. Okay, so I personally only have one wife. I don't know, some of you might have more than one, so therefore I am monogamous. You're doing the same thing over and over and over again. Monotonous, that's what the word means. Mono always means one. Okay? I have one term in an algebraic statement. X could be x squared, could be 3xy. That's called a monomial. Okay, so now I have two things. I have two legs. Technically, I have 2 feet. So I am a biped. Good. I ride something that has 2 wheels. And it's called a bicycle. I'm telling you what to do. Our conversation is unilateral. We're going back and forth. It's called bilateral. Some people don't realize that's what that means. Now in math, when we cut a line segment exactly in half, or we cut an angle exactly in half, we call that bisecting. 7th grade science, you cut remember the cat, and you cut the cat. You didn't bisect the cat.
Dissect.
You dissected. What's the difference? Well, the implication is you're not cutting it exactly in half, but you are cutting it into 2. Die. I'm dissolving my business partners. I'm dissolving my marriage. That's called a divorce.
Oh, you meant you weren't.
Oh, two roads
diverged
diverged into a wood and I took the one less traveled by, and that has made all the difference. Greatest poem ever written, Robert Frost. Diverge means there's two different paths and they never coincide or intersect. So die means two, but it's usually got a different connotation. In math, we rarely use die. We usually use by because there's an implication of, half. But in chemistry, if I have two of something, we don't say by, we say
Die.
die. So hydrogen dioxide.
H2.
Well, no, that'd be HO2.
Oh, sorry.
H2O would be dihydrogen oxide, but we say die.
Okay.
Now, you've lost the use of two of your limbs. Usually it would be your legs, not your arms.
Paraplegic.
You have two lines maybe running in the same direction.
Para.
Para. That means two. A lot of people don't realize. So you lost the use of two legs, you are a
Paraplegic.
paraplegic. People don't, a lot of folks don't realize that's what these words mean. They are from math words, they're Latin words. Three, that's easy, there's only one.
Try.
Oh, by the way, you like to run, swim, and
Triathlon.
bicycle.
Triathlon.
You're a triathlete. In the Winter Olympics, there's an event that only has two things. This is the craziest one. This is my favorite, maybe, of all events. This is the one where you ski for a little while, and then you pull the rifle off your back and you shoot things. And then you cross-country ski for a little while, and you shoot more things. It's maybe the most popular event in any Nordic country. It's called the biathlon. Yeah, it's an Olympic event. Ski and shoot things? Yeah, you think from a James Bond movie or something. No. So, in three, try. That's easy. Triangle. Four, now four's a little trickier. Okay, I have a two-stranded muscle on the top of my arm called a biceps. I have a three-stranded muscle on the back of my arm called a triceps. There's actually an S at the end, most people don't realize that. I have a four-stranded muscle on the top of my thighs called a quadriceps. I have a four-sided figure in two dimensions called a quadrilateral. Oh, what's quad? Four. Problem is, I have a three-dimensional shape that's defined by 3 points in space that are not on the same plane. It's not a quadrilateral. Polygons use the gon. Decagon, hexagon, all that. That means two-dimensional. Hedron is what we use if it's three-dimensional. This is not a quadrahedron. Okay, how many have ever had to take an antibiotic in their lifetime? Okay, does anybody not take penicillin? I can't do penicillin. I had an allergic reaction a million years ago and now I can't because it will kill me. So the most common antibiotic if you're not taking penicillin?
Isn't it like that?
How many of you have heard of tetracycline? Now it's less common than it used to be, but that used to be the only other one anybody gave for a generation. Now they got a million versions of it, the zithromycin, anything with mycin. Tetra. So that shape that I just drew, it's called a tetrahedron. It's the simplest three-dimensional shape there is because I only need 4 unique points. Do we use tetra? Chemistry. You don't use quad in chemistry, you'll hear tetra for cycle. 5, now 5's a little bit tricky. Okay, a 5-sided figure, the 5-sided building in Washington where all the generals meet is called the Pentagon. Right? I know what a pentagon is. It's a 5-sided figure. Pent. But if you had 3 babies at one time, we call those triplets. If you have 4 at one time, we call them quadruplets. If you have 5 at one time, we don't call them penta-somethings. We call them quintuplets. Quint. It's less common. Pent is more mathematical. Now, 6 and 7 are the trickiest ones of all. These throw everybody for a loop, and this has to do with Latin. Okay, does anyone here speak Japanese or know any Japanese words? Okay, there's many, many, many Japanese words where the G and the K mean the same thing. For example, I taught martial arts for 40 years. A kick is, you use keri, K-E-R-I, or you use geri, G-E-R-I. There are many words in Japanese where the G or the K means the exact same word. And it gets confusing when you're trying to learn vocab because it's a context. Well, in Latin, it turns out the H and the S. There are many words, the exact same word, H and S mean the exact same thing, but it's a context thing. there are two prefixes for 6. Now, I have a 6-sided figure. That's called a hexagon. Everybody knows that, but a far more common version. Okay, you're in your 40s, you are a quadragenarian. You're in your 50s, you're a quintagenarian, and maybe the coolest name of all. If you're in your 60s, you're a sexygenarian. That's not a joke, that's the word. Because the other and far more common, sex. That's Latin for 6. If you have 6 babies at one time, they're not hextuplets, they are sextuplets. Oh, the S and the H, like I was just saying. So 7 is really tricky. A 7-sided figure is generally called a septagon. I have heard people say heptagon, that's actually not a word, but it's okay. Now in the Olympics, you guys all know, we just had an Olympics. The men compete in an event that they do 10 things, and we always label that the winner, the world's greatest athlete. The women have similar thing, but it only has 7 events. Does anybody know what that one's called? I'll give you a hint. You just said sept. It's called the heptathlon. The heptathlon, which means 7. Now you're going to love this one. Okay, 8, that's easy. 8-sided, the stop sign. Think of that creature in the ocean that has 8 limbs. It's called a octopus. Right? If you're into the whole MMA thing, they don't fight in a pentagon, they fight in an octagon. What does octa mean? 8. That one's pretty easy for most people. Now, I have fun with this one. I figured this out as a kid because I had a lot of spare time because I was usually not in the classrooms. But as a child, I remember doing some reading, I figured this out. By the way, the original calendar that the Romans used did not have 12 months in it, only had 10. A lot of people don't realize this. They named 2 months after Caesar's. They named one of the months after Julius and another one after Augustus. You'd never figure out what those months were, though. Julius and Augustus. What do you think those months were? So what was the original 7th month? September. What was the original 8th month? October. 9th month? November. The original 10th month? December. I think I was about 7 when I figured that one out, and most adults still don't realize that. The months were named after the Latin. Romans, that's Latin, comes from the Romans. 9, nov, and non. A nonagon is a 9-sided figure. Nonagenarian is someone in their 90s, not a lot of those. That's probably the most obscure, but maybe the most common of all of them then would be 10. Well, the 10 is a little bit tricky because it's kind of a context thing. DEC, what's 10 years? A decade. Okay. What is 10 meters? It's confusing. That's a decameter, that's CK. A tenth of a meter is a decimeter. So DEC is a little tricky. It means 10, but in some contexts it can mean 1/10. Decimal. Oh, but sound is the decibel system, and that's a scale of 10. Remember, it's logarithm of base 10. So usually when you see DEC, it usually means 10, but it can mean 10. Okay, what's 100? Okay, you got 100 pennies in your pocket. 100 years? Century. A little critter with supposedly 100 legs? Now this is my favorite because again, my entire life I've never met one person who knew this one, but you all should. The Roman commander of exactly 100 soldiers?
Centurion. A
centurion. People. That's why they call them that. Cent means 100. But what's a centimeter?
100.
It's 100th. So in context, metric particularly, cent can mean 100th in the context. So when you see cent, that means 100. What's 1,000? No. What's 1,000 years? That's always relate. 1,000 years is a millennium. Oh, okay. But 1/1000th, we also use mil. Context. Now the last thing I'm going to show you, oh, by the way, there is one other one. A half of a circle is called a semicircle. What's a half of a sphere called? We don't call it a semisphere, we call it a
hemisphere.
Hemisphere, H and S again. Nobody says hemicircle or semisphere, but could you?
Sure.
because they actually both mean the same thing, but it's a context. We say hemi when it's three-dimensional, we say semi when it's two, but they both mean half. Half circle or half sphere. Again, do you need to know this in a math sense? Oh my goodness, the most common shape we're going to use in Calc 3 is a hemisphere. But one of the most common shapes we're going to use in here is a semicircle. We need to know what it means. Now the last one I'll just have some fun with. You'll love this. Again, this is one of these things that when you have a lot of time on your hands, when do we put the comma in a number? After 1,000. So when do we put the next comma? After 1,000 thousands. When do we put the next one? After 1,000 squared thousands. Wait, what's 1,000 thousands? A million. 1,000 squared thousands? A billion. Trillion. Quadrillion. Quintillion. Sextillion. Septillion. Octillion. Novillion. That's where those come from. People. A billion is 1,000 squared thousands. A trillion is 1,000 cubed thousands. A quadrillion is it's actually that simple. You go, oh my goodness. How many have had chemistry again? What's Avogadro's number? 6.02 times 10 to the 23rd. So therefore, what would that be if I wanted to actually name it? Give a little extra assignment. So it's not billions, is it trillions, is it quadrillions, is it quintillions? It's one of those things, isn't it? You've got to count the sections of threes. If you don't know what the vocab is, sometimes you won't be able to answer the question. And most of you, well, no, not most of you, a lot of you will have chemistry. Most of you will probably have physics. How many have to do both, by the way? Okay, most of you. You need to know these things for those classes, and you're never going to learn them in those classes. They actually expect you to walk in knowing this, but where would you have seen this? That's the thing I find troubling, is this is really important information, because if you don't know the naming of things in chemistry, that could be a problem. And the last thing I'll leave you with, I did take high school chemistry from a very, very eccentric person. I mean, it's literally nuts. And every day before class, he made us recite the exact same verse every single day. Johnny was a chemist's son, Johnny is no more. What he thought was H2O was H2SO4. We had to recite that every single day for a whole year. What's the point? H2SO4 is sulfuric acid. It looks and smells exactly the same as water. So it was basically be careful in the lab when we're doing experiments. It was kind of corny, but you know what? I still remember it, 150 years later, so maybe it was a good idea. All right, go ahead and press the red button there.